In this video, I'm going to explain how to determine shape of molecules using the valence shell electron pair repulsion model or VSEPR model. Why it's important to know about shape of molecules? If you know shape of molecules, then we can talk about their properties. But what's the VSEPR model? Let's look at the molecule. If I have a molecule like, okay, if you look at this molecule, our central atom is gray. And VSEPR model talk about electrons, pair electrons around the central atom. So if I want to see how many pairs I have around my central atom, I can say one pair here and one pair. So because electrons repel each other, definitely these electrons want to be as far as possible. So when I have two pairs of electrons around the central atom, so what the shape can be, something that we discussed today. And also let's look at the other molecule like VCl3. So our central atom is full. And we take a look at pairs of electrons here. So we have this here, we have one pair here, and we have. And we need to find out what shape makes these three pairs of electrons to be as far as possible to minimize repulsion force. If I have two nodes that are tied back, you see the point that I tied to node actually is like central atom. And each balloon is like one pair of electrons. Right now, if I leave this one on my hand, you see the shape that it makes is leaf. If I have three balloons that are tied in, again, you see the place that are tied three balloons is my central atom. And then I have three groups of electrons around. And these three groups of electrons want to be as far as possible. The shape that they make is similar to this one. And if we measure the angle between them, it's about 120 degrees. Or we can show the molecule like this, and you see the purple one is the central atom, and it has three bonds with three different atoms. And the shape, if I put it on my hand, you see it sit on the plane, so it's not three-dimensional. And the angle is 120. Let's take a close look at each one. So if we have two pairs, if this one is central atom, and if we have two pairs of electrons around that, the shape that they make is linear, and the angle is 180. One example for this bond can be carbon dioxide, and be BE. Yet, and as a result, the angle is 180 degrees. If you have three pairs of electrons around your central atom, the shape that they make, as you can see, if I say this one is central atom, so this is one bond, second bond, and third. This is the shape that they make. And the angle between each of these is 120 degrees. As one example, we can talk about VCl3. And then the shape that we name trigonal plane. The next molecule that I want to talk is about CCF4 or CCF4. CCF4. The first thing, always, if you want to find the shape of molecule, first you need to draw a Lewis diagram for that. So I write the central atom and the other elements around. Other atoms, we have 4 chlorine, and with the electrons. as you can see, around the central atom, we have 4 pairs of electrons. And if they want to be as far as possible, the shape that they make is tetrahedral, and the angle is about 109.5. But how I can draw this molecule? Because you see this molecule is 3-dimensional. If I want to draw a 3-dimensional molecule, how I can draw it on a piece of paper? Something that we need to do. We write our central atom, and then we know for this molecule, I can say this one. If I have a page, if I put a page through here, this one and this one are on the same page or on the same plane, but this one is at the back of the page, and this one is the front. So something that I do for those that they are on the plane, just I use simple lines. Just I write here and here. And then for that one that is at the back of the page, I use dashed line for back of the page. And I write here. And for that one that is in front of something like a triangle, visible, and I write here. So by drawing this way, as soon as someone look at the molecule, they know these two are at the same plane. This one is at the back and this one is in front. And you get some idea of 3-dimensional shape. The next molecules that I want to do is this molecule that is the central atom and 1, 2, 3, 4, 5 pairs of electrons around that. As you can see, this molecule the name is trigonal bipyramidal, and one example is PCl5. So I can write it like Cl and 1. So these 3 are on one plane. This one is above and this one is below. And effectively to put electrons. And if we have 6 groups of electrons or 6 pairs of electrons around the central atom, the shape is octahedral. If I want to give you one example, I can say S6, and it's like S, and 1. So these 4 are on the plane, this one is above, and this one is below. The other example that I like to go through is NH3. First, I write CCl4 one more time because we need to compare it. So for CCl4, Lewis diagram is like this. And the shape that we talked about was tetrahedral. And we know we can draw it somehow to show that it's 3-dimensional, and angle was 1.9. The other molecule that I want to talk about is NF3 or NH3. If I write Lewis diagram for NF3, it's like this, and F, F, and 2 electrons. something that I can see here. I see around the nitrogen, definitely I have four groups. Let's see, four groups of electrons. We know four groups of electrons should be tetrahedral. But here we have this pair of electrons between nitrogen and fluorine. This pair the same, this pair the same. But this pair is non-bonding. So if you want to say it's similar to tetrahedral, so I put this one like, okay, let's say, and here because we don't have any atom, just we have pair of electrons. So it can't be tetrahedral. But on the other hand, we know these electrons are all bonding electrons. But this one is non-bonding. The repulsion force between non-bonding electron and bonding electron is larger than repulsion force between bonding electron and bonding electron. So as a result, this repulsion force between this non-bonding and bonding is larger than repulsion force between these two and these two. As a result, it looks like that this electron push this bond a little bit closer to each other because it applies a bigger force. So as a result, the angle here, instead of being 109.5 like tetrahedral, the angle is actually 107 degrees. So for NS3, the shape is pyramidal and the angle is 107, and the reason is this non-bonding electron. We need to remember always the repulsion force between non-bonding electrons are larger than non-bonding bonding and larger than bonding. So we go through one more example. That's what it's H2O. Okay. Again, when I look at this molecule, I see, okay, I have one group, two groups, three, four. And we learned that four groups should be tetrahedral. But four, we don't have four atoms. So the shape, what's the shape here? Okay, it means that we cut two bonds here, two bonds of CCl4. So it should be something like this bar and this one. Sorry, my drawing is terrible. Okay. The shape that it should be. But actually, when we look at it, so I draw it this way firstly, and then we talk about the angle. And don't forget non-parabolic. Right, that's something that we can see here. Actually, see we have non-bonding electron, and we see here that it has the largest repulsion force. So these want to be really far away from each other. And then we have here non-bonding bonding and bonding. So repulsion between these two is the largest. After that, repulsion between non-bonding and bonding is non-bonding and bonding. And the smallest one is the repulsion between bonding electrons. So it means these non-bonding electrons actually push these two bonds even closer to each other. So the angle becomes even smaller than 107 and become 104.5. And the shape is bent.